So let's get started. Welcome to the third workshop in this series, Beauty of Noises. First, I'll show you some of the daily sketches that I've done that I used noises. I'll start all the way from one of the first few sketches that I created in early in January. So this is essentially just a blob. And then I used the noise function to create like a natural movement. So it's like a bubble that moves naturally. And looking at the sketches, you can see how I progress in a lot of those sketches. So because I'm trying to do it every day, so that every day I make a small change. Usually for about 2-3 weeks, I'll be working on very similar things, but every day I'm trying to change something different, be it changing the color or maybe change some of the values. So I started with something as simple as this, and then I played around with it in various formats, like this one. And so these are what I use noises for. And then there's this rotations, like little squares that rotates and changes color. That's also something that I use noises for, because if I were to use random, it would just be very chaotic. But with noise, you see that like a very natural and as if like it's water or clouds, that kind of vibe. So, and also this is just a simple like curve or a stroke that moves based on some noise value. Okay. So these are just some of the possibilities that you have by using noise. But what exactly is noise? Noise, or more specifically, what we'll be using is called Perlin noise. Is a type of is an algorithm that generates a natural smooth patterns. So as you can read from the history, Ken Perlin was frustrated with like the machine-like look of the computer generated imagery. So he developed his own algorithm, and he even was awarded Academy Award for technical achievement. So so even if you are just learning code, you can actually possibly earn Academy Award one day. And I hope, like if any one of you earn an Academy Award at some point, let me know. I'll be really, really proud and really happy to see that happen. So that's a little bit of history. And let's bring back to the context of P5.js. Let's take a quick look at how their official reference defines noise. It returns the Perlin noise value at a specified coordinates. So essentially, the noise function is almost similar to like a sine function, because what sine function does is to return a sine value based on the input that you provide. So when you think about the sine wave, you are providing the x value and you are trying to get the y value from the sine function. So the noise function, you can also provide some sort of x value, and then you will get a y value. So let's take a look at a comparison between between random function, noise function, and sine function. Okay, I'll make this a little smaller. So you can see the top one is a random function, and then the bottom one is sine function, the sine wave. So as you are giving the x value, random function simply doesn't take a x value. It simply, give you a random value. So that's why it's really spread out and random. And the sine wave at the bottom, as x increases, the y goes up and down very smoothly. So the sine or cosine can also be helpful to create like very smooth animation, but it is, it is more natural than random. However, it's also, it keep repeat the exact same position, same movement. So however, if you look at the noise function, that provides a more natural movement. Imagine if it's be it a pattern or if it's something that's moving around, it's more likely to resemble the second, which is a noise function instead of either of the other two. Question?
So yeah, I know you've explained it and I do understand, I think, but is it that the noise function takes into account the value before it, so that it's not jumping all over the place?
Sort of. So no, the noise function, it's actually very close to the sine function. So for instance, when you look at the sine function, it's not so much about it's considering the previous function. It's just because the sine function, as a mathematical formula, the way it's designed is that, it moves smoothly up and down. The noise function, in a way, you can almost essentially can Perlin design this function so that there's multiple math that is under the hood, so that whenever you provide an input, as the input increases, the output increase or decrease in a more smooth or more natural manner.
So it's dependent on your input.
Yeah, so it's more dependent on your input. And the input, so imagine this Perlin noise is actually almost like a predefined like a grid. And so as you are picking whatever input is, like think of that as x-axis. If you are picking any x-axis, it will give you the y-axis of the value. Okay? And that's sort of the most basic, which is the 1D Perlin noise. But then you can also provide multiple input. So if you have two input, it's as if this noise values are stored in like a 2D space. And then there's also 3D. So essentially, they're like those values that already calculated. So any values that in between is like close to each other. And then what you are doing is just to provide like an index to try to access those values. Does that make sense?
Yeah.
Okay. Thank you. So that's the differences, and then let's take a look at what we will be doing today. Remember how we have the colorful ribbon from previous workshop? If we add Perlin noise, it looks more like a cloud. I mean, of course, this moves more horizontally, but if you turn it to move vertically, it might look like cloud or something that's a little bit different. So it's not as repetitive as the sine wave, and it changes in a more different way. Did you have a question earlier or no? Okay, cool. So that's one thing. That will be a very small change. It will be based on the code that we created from the previous class. And then let me stop this one. And then we also have one that was 1D. So essentially, by changing the that was just to apply the noise function to, I believe I applied it to the size, I think. Oh, actually, I applied the noise function in the y-axis. So it's the movement that has noise applied. And then in this second one we will be working on, right now it's a smiley face. I mean, this one, you can use both 1D and 2D to implement this. Essentially, you are using noise function for both the x value and y value, and then it generate like a movement like in this 2D space. I was also using this smiley face that I created previously. But again, if you have your own function, you can create whatever that you like. And later we will have 2D, 3D noise. So this is 3D because first it's on a 2D space, and then over time it also changes. So that's where the 3D come from. That's what the 3D is referring to. Again, I'll show all this code. So I designed it so that there's sliders where you can play around and try it out, so that when you have less sort of pixels or larger cubes versus when you have really small cubes, and then you can change different settings, different level of detail, like less detail, there's finer details, and you can add color, or you can switch between different mode. Let me make this a little bigger. So this is more of a pie shape, and there's a rotating squares, so you can, once you learn noise, you can use it in many different ways. Okay, and lastly, depending on how much time we have, we might learn how to create a simple blob. Okay, again, these examples, I'll share all of this with you so that if you want to figure out, if you want to learn how I created them, you can read the code of this. Okay, so let's get to the coding. First, as a refresher, let's recreate the. If you already have it, feel free to open that one, or I'll demonstrate how we can recreate the colorful ribbon that we created in the last workshop. I'll give my project a name, workshop 3, colorful ribbon with noise. And this time, instead of horizontal, I'll create a ribbon vertically. I'll draw circles. Actually start with a for loop. So I'll go really quickly because this is what we've covered in the previous workshop already. So let I, or maybe I'll use y because it's y-axis, y equal to 0, y smaller than 400, which is the height of the canvas, and y plus plus, so it will increase, and I'll draw a circle at the middle of the in the middle of the canvas, and then the y value for the y, and for the size we are going to use a sine wave, so 200 times sine and I, actually y. Let's take a look. Okay, and then this needs to be divided by maybe 50, and y position, the x position, I'm also going to apply this over there. Okay, that's a little bit too much, maybe about 50. This also maybe about 100, and then we can add frame count to animate this, so 50, and also animate the size, frame count divided by 50. Okay, that's I think usually you don't want the numbers to be the same, so it looks more natural. For maybe 30 for this one, and I'll turn off the stroke. Okay, I'm going to add a fill color, which is again I'm going to use sine. Actually, here I'm going to introduce a new function. Instead of previously I did some math to convert the sine function output to 0 to 255 for the color. There's actually a very handy built-in function of P5 that does all the math for you, which is called map. So what map does is to map a value, a range of value, to a new range. So the sine output, the output for sine function is from -1 to +1, +1, and the value we want is a number from 0 to 255. So what we can do is use this map function to achieve that. So map and then the value that you want to map, which is a sine and y divided by 50. And so that's the first argument that you provide for the map function. So sine y divided by 50, and then minus 1, which is the smallest value, original value that you are trying to map from, and then to 0 to 55, that's the final value that you want to map to. I think I made a mistake. Yeah, so I missed a parenthesis. So let me also tidy code. Essentially, I have the sine function right here, which provides the output of -1 to +1. So I specify here -1 to +1, and I want to map this value, proportionally map this value to on a scale from 0 to 255. Okay, I'm going to do this for all RGB. Okay, and I'm going to change the numbers slightly differently so that they're colorful. Okay, and if I want to add further color change, I can add the frame count divided by something to each of the function, each of the sine function input. 40, 30. Okay, so that changed color over time. As you can see, because I'm not using the exact same number each time, so every time I create this is something slightly different. Any questions so far? So far I just recreated the same colorful ribbon that we made from the previous workshop. The only thing that's new is a map function. That's an easier way for you to map one value to a different range of values. Okay, so how can we add noise? One simple way is to simply replace one of the sine function with the noise function. So let's see, if we want to add noise to the x axis, the x value, we can change the sign to noise. You see it's already different. Yeah. The noise function normally or by default, it produces a value from 0 to 1. So that's where one thing that's different from sine. Sine produces a value from -1 to 1. But noise always produces a value from 0 to 1. So you can either multiply it by a number, or you can use the map function to map to a different range. I like a number that's anywhere from 0 to 50, so I can multiply this noise function by 50, or if you want to have bigger changes, I can multiply it by 100. Okay. And because this function is only positive, you see how right now the larger the number is, the more to the right this cloudy thing is. So if you want it to be more towards the center, because width divided by 2 is already the center, you are essentially adding a positive number onto the center, so it's only going to move further to the right. So if you want it to be center, again, you can do math on your own, or you can use the map function. So map, I put the noise function inside. So map that noise function from a number from 0 to 1 to a number from -50 to +50. So now it's more centrally located. Okay? Any questions? So that's our first attempt of using noise. Essentially, if you know how to use the sine function already, simply replace that sine function, and that produce a noise value that changes. Okay, so similarly, If we want to add the noise function, apply the noise function to the size of the circles, you can change that sign to noise. Yeah. One thing to keep in mind is by default, the noise function usually produces a value that's sort of in the middle, so it's almost never gets so close to 0 or too close to 1. It's usually a number that's more, around the 0.5, yeah, above or below. So that's why when I switch to noise, yeah, this the changes between the circles is not as big as when we were using sine. Okay. However, what we can do is to have control over this noise function, and that is called noise detail. So that you can add in setup. You can set it once and forget about it, or not worry about it. So in setup, there's a function called noise detail. And noise detail, there are two values two arguments that you want to provide. The first one is the level of details. So it needs to be an integer. Let's say 1. When you use 1, that has very low level details, meaning the changes between the circles is very subtle, very small, very smooth. So it's almost, in a way, it's almost as smooth as sine or cosine function. And the larger the number is, the more subtle, small movements or noises that you see. Yeah. Basically, the larger the number, the noisier the output is. And then there's a second value, which is called a fall off. Essentially, the larger for that, it's quite similar. The larger the value, the larger the noisier the output will be. However, usually by default it's 0.5. But if you have a value and usually you want to keep it below 0.5 or below 1. If the value is too big, the output, so remember how I said noise function usually produce a value from 0 to 1. However, if you set the fall off to a number bigger than 0.5, it's possible to produce a number that's larger than 1. To understand exactly how it works, you can read the Wikipedia article, or you can try to read the description of how the noise function works. Okay. See how if I increase this value, this is getting really large. So I multiply the noise function by 100, but I'm pretty sure some of the circles is larger than 100 at this point. Yeah. So, if that's what you want, that's totally fine. But usually, if you want to have control over the sizes, use a number that's smaller than 0.5, so that it will never reach a number that's bigger than the number that you specified. Okay. Again, you can always refer back to the function that I created. Let's see. You can use this sketch that I created to play with the values. So with the same noise function, if I decrease the level of detail, you see it's smoother transitions. And as I increase the level of detail, you see more noises. And this is the fall off. As I decrease the fall off, very similar effect. And as I increase, if I increase a lot, it becomes almost pure white. That's because now the value is larger than 255. Okay. So this is how this is one sketch that can help visualize the noise. Okay. And that's it for this first section. Any questions for now? Yeah? No? Good. So now let's move on to 2D noise, or how you can use 1D noise to create something move something 2D, because right now at the moment we are either changing the size or we are changing on one axis of the you applying noise in one axis. How can we apply noise in two axes? I'll start a new sketch, give it a name, workshop number 3, 2D noise. Okay, and this time we would recreate this movement that I created earlier. Essentially, we can create again a circle, but let's make this circle move in a 2D space. What do you need for a circle? You need x and y. So why don't we use a noise function for both x and y? So noise, noise, comma, and give it a size, maybe 50. Right now, it doesn't really show anything. That's because we haven't provided an input for the noise function. So let's try with a number, maybe 10, and then 20 for the next value. You see how it's on the top left? That's because, again, the noise function, by default, the output is 0 to 1. So it's very, very small. That's why it's very close to the origin. So I'll simply multiply this by the size of the canvas, 400, or you can use width or height. Okay. So essentially, I'm using noise 10 and noise 20 for both the x, I'm using a noise function for both the x and y value for the circle. Yeah. And also notice how every time, this is almost similar to a random function. Every time I refresh, I'm using the shortcut command enter. Every time I refresh, it goes to a different location. So every time when you are using the noise function, like it also similar to the random, it has random seed. The noise also uses a noise seed that generate that noise space, and then you can use those values to access that noise, the noise values at all the accesses. So even though I provide the same input, 10 and 20 for the noise, it gives a different result because every time it's using a different seed. We can specify that seed with noise seed and give it a number. It can be any number. So now it's going to be fixed because we are providing that seed. Okay. However, we do want this circle to move instead of staying at one spot. How do you make something move? You change this number to a variable. And the most, easy option is to use frame count. So I'm going to change one of the input for noise to frame count. You'll see how it moves really, really fast. So because frame count changes by 1 every time, and that actually produced almost a random-like result. That's because you are jumping too much in the noise space. So instead of directly using frame count, you can divide frame count by maybe 10. Now this is a little smoother. And then 20, this is 30, even smoother, or 50, that's even smoother. Okay? So far, it just moves on the x-axis, depending on, the output the noise gives. Yeah. And remember, because we have the noise seed, so every time you refresh, it would start from the same spot. It would, even though it's a output provided by generated with noise, but you are able to create the exact same pattern, exact same movement each time. Yeah. And if that's not something you want, then you can simply not specify noise seed, so that every time it create a new pattern. Okay, so this is just for the x, and then you can do the same thing for y. Frame count divided by 50. Notice how now it's moving on the diagonal. of the canvas. That's because we're providing the same value, same input to noise. Okay, because each time we run it, the noise space is the same, and so whenever you give the same input, it will always produce the same output. And this is where we need to work with 2D noise. One simple way we can utilize 1D noise for this 2D space is that you can simply shift one of the noise to a different spot. What I mean by that is one of the noise is frame count divided by 50, the other one is frame count divided by 50, and then you can add maybe 100. That means even though it's the same noise function, they are moving at a different portion of the noise. So it still creates a fact that it's 2D, but even though we are just using that same 1D noise, we are sort of selecting a different portion, one for X and one for Y. Okay, and what happened with this is, I think sometimes it might. That's okay. You might notice some repetition because of this. I think it's hard to see from here. But either way, so that's one option. You can use different noise, a different portion of the noise, or you can simply use 2D noise, meaning there's two values you can provide. So two argument that you give to the noise function. So the first one, you have frame count divided by 50. Let's actually get back to the previous state. So they are moving at the same spot. What you can do is provide additional axis coordinate. Let's say the first one is 0, which is right now the same. Now if you simply add comma a 1 to the second one, now the second one moves at a different direction. And that's because, again, when you have that sort of grid of noises, one of them is using this stream, and then you shift this around. The other one, the noise function, is using a different stream of the noise values. Okay? And if you like to have leave the trace, you can move the background to setup so that you can actually see what the noise function is generating for you. And this is also one example where you can use a noise function to actually generate a drawing or a pattern. Okay? And depending on the noise, depending on how you are, how much you are scaling this and what noise seed you are providing, you will generate a different pattern each time. Yes?
Yeah, noise seed. What's the range? Is it 0 to...
It's for the input?
Yeah.
For the input, as far as I know, it's infinite. You can, it can go really, because I think it's designed in a way so that you can, keep going, essentially, whatever the computer allows. When you're working with programming, usually there's like a maximum number that a variable can hold. That's just because of the limit of the computer. Then that's the only limit that I'm aware of. Yeah. Okay. And one other thing to note is you usually do want to provide a value that is only positive, and that's because the noises are symmetrical on the other space, on the negative space. So if you are using a value from negative to positive, it would mirror the same movement, like in the opposite direction. So usually that's not something we want, but if that's what you're trying to create, something that moves in reverse, that's fine. But that's just something to keep in mind. Yeah. So, and similarly, you can also do 3D noise, which we will get into in a second. And you can add noise to the color as well. so that this is not just a movement of the noise, it's also so the color is also changes based on the noise. So that's also something else you can do. And let's see. So let's try run this again. You see how it moves this pattern. Run this again. It's the same pattern. And if you change the noise seed, it starts from somewhere completely differently and moves differently. Okay. However, with the same noise seed, you create something that moves the exact same spot. Okay. One other new tip for generating movements is to use the alpha value. So when we're working with colors, we've only been using the RGB. Actually, there's a fourth value that you can use that's referred to as alpha, which is the transparency of the color. And if you apply transparency to the background in particular, you actually have a nice effect where the movement that you have actually leave a trace, but it only apparent for a couple frames and it will disappear. So let's take a look. So it's 220. So when you have three values, that's the fourth value. Or if you have one value for darkness, you simply need to provide one additional value for the transparency. It will be a transparent gray. So let's say if we add transparency, is also by default is a value from 0 to 255. So I'm going to add 100. And now you see how it leaves a trace. Maybe I'll make this value even smaller. Now it leaves a longer trace, or maybe even smaller. Okay. I think this is something that I haven't figured out, which is when you have when the number is too small, the trace it's left there is actually permanent. That I think it has something to do with how this transparency thing works. So usually you can test out a couple of different values. If it's large enough, then it should not leave a permanent trace. So even right now, I think I can see a very subtle trace there. But if it's a fairly large value, it should not leave a trace. Yeah. Okay. Any questions so far? No. So let's move on to two-dimensional noise in like a grid. So again, new sketch, workshop number 3, and noise grid. Okay. Start from new sketch, and what we want is let's make this a little bigger. Is to use some for loops to create a grid of squares. So let's use create a for loop. So for let x. So by convention, we usually use a number variable either I for index or j. Anything that follows I. However, this time I'm literally using this as the x and y position of the x and y position on x and y coordinate on the canvas. So that's why I'm using x and y instead. So let x equal to 0. X is smaller than width, or just to simplify, x smaller than 400, and then x plus plus. So this is x plus plus is a shorthand for x equal to x plus 1. Because this is used so often, it can be shorted as x plus plus. Okay, it basically does the same thing. And in our case, actually, we don't want the increment to be 1, so we do want to have the more complete version. And there's another shorthand. If you simply want to increment a variable by a certain number, you can also do x plus equal to a number. Let's say 10. What that does is increment x by 10, meaning x equals to x plus 10. And that's x. And then inside of the for loop, you can write another for loop for y. Maybe before I write that for loop, I'll just demonstrate what the x does. So we can draw a square at the x location, and then the y location, I'll specify it as 0 for now. And then the size would be the increment, so 10. I'm also going to round the corner by 3, with the radius of 3. So you see I have a row of rectangles on top. Okay? And we can change this number 10 to 20. Remember to change it both at the size and in the increment. And then we have a line of rectangle that's slightly bigger. Okay. And now, if we want a complete grid of rectangles or squares, we need to add another for loop inside. So for each column, we want to draw multiple rows. So we can add a for loop, let y equals to 0, and y smaller than, lowercase y smaller than 400, and y plus equals to 20. And then you want to put this square inside of both of the for loops. Okay? And instead of 0, we can use y now. So now we have a grid. Okay? So far, so good. And just to make it a little more fun, we can control the size of the square with a variable. I'll use a global variable for this. So let size equal to maybe 50. Okay. So now we have this size variable that holds the value of the size of the square, and then we can use this variable instead of what's called the magic numbers, meaning a number that you magically decide. Now if we use variables, I replace all the 20s with size and also the 20 for the size of the square. Now if I run this, okay, reserved function. Okay, so this friendly message actually remind me that size is already a function name. So let's try to use something else. Maybe I'll just put square size, or square size instead. I'm going to do that shortcut, Command D, select the value, the word or the variable that you want to change, and then Command D to select all of them, and then paste to change them at the same time. Okay, so now if I change the square size on the top of the sketch, the whole sketch changes, based on the variable that I provide. Okay. And I can even use this for the rounded corner as well. So instead of size, I want to multiply it by maybe 0.2. So it's proportionally, the corner is proportionally sized based on the size of the square. Okay? Everyone's following so far? Yeah? And finally, where does the noise come in? We can try to use color for the noise. We can use noise for the fill color. So fill And for now, let's just work with gray value. So 255 times noise. Remember, noise is 0 to 1. So inside of the noise, now we have two axes, so we can simply put x and y. Okay. So based on the x and y, noise provide a value from 0 to 1, and it's multiplied by 255, so we can use that for as the fill color. Okay. And then there's a couple ways that you can adjust this. Maybe we should first make it a little bit smaller so it's easier to see those noise. So now it's literally just look like noisy. But if you want the noise to be smoother, you can reduce the increment by multiply the x and y to multiply x by 0.5 and multiply y 0.1 and 0.1, or maybe I'll make it even smaller, 0.01. So now that's smoother. So the smaller the changes are between each square, the smoother the value will be. Okay. And then we can always use the noise detail function in setup to decide on how smooth you want it to be. So 1.5, that's super smooth. 2, that's a little more noisier. 3, even noisier. 4, 5 become more and more noisy. Okay. So this provide like a building block for many different things. I'm using it for color. Now you can use it for many different things. I can use it for the rounded corner of the square. I can use it for some kind of rotation. I can use it for the size. And you know, the basically the possibilities are infinite. So let's try a couple of things that we can use this for. And before we do that, let's actually try to make this move. Okay, so this one is a noise grid that's static, that does not move. So that's why we have just 2D, x and y. I'll adjust the name a little bit. Static noise grid. And I'm going to duplicate this. So in File, and there's a duplicate option. I want to create the essentially duplicate this sketch so you have the same sketch, but you save the previous sketch. So in case you want to go back and work with that one again. So now I'm going to make this a moving or animated noise grid. And in order to do that, it's very similar to what we've done in the past. We can use frame count as a z-axis. Maybe I'll tidy code so it's a little easier to read. So inside fill, inside the noise of the fill, we have x and y, and then we can add additional one, frame count. Again, now if you just change by 1 every time, it's going to be super fast. You can divide it by 100 or times 0.001. This is where it gets a lot smoother and moves. Okay, so divided by 100 or times 0.01. Okay, so now you have something moving. Yeah, and this will be that building block for you to do a lot of animated, interesting animated things. Okay, so let's try a couple of things that I mentioned before. You know, we can apply this to the size. I'm going to simply copy this noise function. Be careful what you're copying. So the parentheses after noise and also the closing parentheses. Make sure you copy all that part. And maybe I'll multiply the square size with this. So you see how the size changes based on the noise. I'm going to make it bigger so it's easier to see. Maybe 40. Yeah. So that's for the size of the square. And we can add this to the rounded corner of the square. So instead of times 0.2, I'll replace the 0.2 with the noise function. Okay. So some of them are, when the rounded corner is the radius of the rounded corner is very big, that's when the square basically turns into a circle. Okay. And for this one, maybe I'll make the circles a little smaller. Okay. And I might want to divide this by 2 to make the changes more obvious. Okay. If there's no questions, we are going to move on to the last part, which is a blob, animated blob. Okay. So let's start a new sketch. Workshop number 3, animated blob. So first, how do we create a blob? That we can use a function called vertex. Essentially, when you're creating a blob, it's not a simple shape like square, circle, triangle. When you need to create a more complicated shape, we need to specify each individual vertexes, and based on the position of the vertex, it will connect the vertex, and it can create different shapes. And there's also 2 types of vertex. Usually you can create with like straight, basically by connecting all the vertexes. That's straight lines. So that's regular vertex. And if you want to create curves, that's something I really like to use, because simply by providing the vertexes, the computer or the P5 sketch will try to find a curve that will go through the vertexes that you provided. So that, give us a very smooth looking shape. So how do you use vertex? Let's start with a simple example. Before we use vertex, you need to write begin shape. So essentially, we are using vertexes to create some kind of a shape. Okay, and then by the end, you will need to write something. You will need to write end shape. So in between, let's add vertexes. So for each vertex, you need to provide x and y. I'm just going to write a few random values. One vertex, it doesn't really do anything. And 2 vertexes, you see how there's a little line here from the first vertex to the second vertex. So I'm going to use values that's a little bit bigger. 200, 200. It's a stroke. And then move on, vertex 200, 300. Okay. And then vertex. So these values, right now I'm just writing random values, so you really don't have to follow the exact values. But essentially what's happening here is that, you can simply provide all the vertexes, and this function will connect all the vertexes into a shape that you want. Yes?
Do you have to specify the first vertex again if you want for the last connection to be made?
Exactly. Yeah. So right now you see how it's open. Let me actually add a stroke, change the stroke weight so it's easier to see. You see how this is not a closed shape. I believe maybe there's also a way to simply close it with like a function. Instead of providing that, I think there's also a closed option. So begin shape p5.js. So, and when you end it, you can specify close. Okay, so that's an even easier way. Okay, to close the shape. And now, how do you create a curve? You simply replace all the vertexes by curve vertex and with a capital V. Okay, again, I'm using Command D to select all of them. I'll change this to curve vertex, and now we have curves. Okay. Maybe I'll change the first one to a different value. Yeah. But with curve vertexes, if you do want to close with end shape close, that simply connect, treat the last vertex as the first vertex as your last vertex to try to close it. That does create like a sharp edge. But when we are creating blobs, I'll show you how you can actually create a smoother vertex. Essentially, you need to not only repeat the first vertex, you also need to, with curve vertexes, there are some additional vertex you need to provide. So even in order to dry, let me turn off this one. Oops, turn off close. Let's take a look. Yeah, so with these many vertexes, it actually only creates a very short curve. That's because additional vertexes is used to control the direction of the vertex. So you need more vertexes, to control the shape. Okay, so if you simply want to close it, you can write close, or you can write those additional ones to create a smooth close. Okay. And how do we do that? That's where our good friends sine and cosine will help us. So I'm going to need write a for loop. So in between begin shape and end shape, we need to write a for loop. And the for loop is going to start from 0 and end at any number that you like, and this will be the number of vertexes that you have. I'm using a for loop to draw the vertexes, so depending on how many vertexes you want to have, you can specify that number here. I'm creating 20 vertices. Yeah, vertices, I guess. And I++ for incrementing I by 1. And inside vertex, what do we want to provide? This is where we'll need to use sine, cosine. Remember how we create a circular gradient with sine and cosine. Basically with the same input, I. If you provide, how should I put this? So essentially with the same input, if you use x, the sine, the output of the sine for the x-axis and output of the cosine for y-axis, that's when you get a circle. However, right now, the circle is too small. We want this to be from the center. So if you want to draw something from the center, you can simply add 200, half of the width and height to the vertex, to the coordinates, or there's another way, which is translate. Translate is a function that moves the origin. So the origin is top left, 0, 0. If you want to move origin to center, width divided by 2, height divided by 2. Okay, now we have a circle in the center, and you also want the circle to be bigger. So 200, this is the radius, so I'll use 100 times sine, 100 times cosine. Okay, this is where you get a circle. However, if you want a complete circle, you want to start from, in terms of the angle, you want to start from 0, you end to 2 pi, because that's 2 pi is 360 degrees, and that's a complete circle. Right now we have value from 0 to 20, and then how can we convert this number to a number that's 0 to 2 pi? Again, we can use the map function that we learned earlier. So this time I'll map the I from 0 to 20 to 0 to 2 pi, 2 underscore pi. Okay? Same map function inside of the cosine. I think I have additional, wait. I missed a semicolon before 2 pi. Let's need to get that, okay. Well, so now that's complete. And I'll change this number to a smaller number. Again, now I have 2 numbers I need to change. That's usually when it would be good if you create a variable. So again, I'll create a variable for the number of vertices. And so that I can simply use that one variable to change that. So maybe I'll start with a small number. So instead of 20, I'll use this variable number of vertices. I need to change both of them. Okay, because we haven't applied curves, so that's why it's a polygon, and because we didn't close it, it sort of start from 0. So when you look at the for loop, number of vertices is 5. It actually starts from 0 and end at 4. It will run 5 times, so it's 0, 1, 2, 3, 4. Okay, so that's why it's not closed. In terms of polygon, you can simply close by adding close to the end shape, but that's not what we want. We can close it by actually increasing the number of vertices. So far, the number is mapped from 0 to number of vertices to 0 to 2 pi, but the I value start from 0 and end at 4. If you want I to reach 5, what you can do is either instead of I smaller than number of vertices, you can write I smaller than or equal to number of vertices, or you can increase this by 1. That means we will run this for loop if I is smaller than number of vertices plus 1, which would be 6. So whenever I is smaller than 6, it will it will keep adding more vertices. Okay, so that's 2 options that you have. Now instead of vertices, let's change this to curve vertex. Remember how curves requires more vertices, so some of them are missing. But because we have already set this up so it's circular, you simply need to draw 2 more vertices. That's by, instead of +1, +3, we change that to +3 so that we are drawing 2 more vertices, and that finishes a complete circle.
What if we don't do like I less than number of vertices plus 1? I mean, instead of that, we use I less than equal number of vertices.
So then that would be, you want to reduce this by 1. Yeah.
Yeah, that will do the same.
Yeah, that will do the same. Okay. So essentially, you have 5 vertices, like 5 vertices of, let's for instance change this to 3. You have the 3 vertices that actually control the shape, but you need 2 additional one when it comes to curves. That's why we are adding this by 2. Okay, so let's say it start from here, the top left, that's the first vertex, second vertex, third vertex, actually fourth vertex, and then fifth and sixth. So actually it needs 3 more. By, adding this equal sign, it adds additional 1, and then plus 2, it adds 2 more. Okay. Any questions? I think this. That's just because how curve works. We can take a look at curve vertex P5JS. So this is what curve vertex looks like. In order to draw this curve, which is 4 points, this is where it draws the 4 points. You actually need to provide what is it? That's 4 points. You actually need to provide 6 vertices. Okay, and we can try this out because the last 2 vertices is really used to control the angle of the curve. That's just because of that math that is going on. Because this curve right here does not need to. Is not like a complete curve, so it simply repeat the first curve vertex and last curve vertex. So let's try to delete this. So if I delete the first one, simply provide this 4, which is exactly the 4 points that we were seeing. If we run this, it only create this curve. Okay, that's just simply how this curve works, because without additional curves, you don't know where this curve should go. Because the curve between this top left corner and the bottom left corner is depend on the next vertex. That's how you can calculate this curve. Does that make any sense?
But
Yeah.
here, like for 4 points, we have like 6, but in our code, we have 3 points.
Yes.
and 6.
Yeah, so we have 3 more. That's because we also need to close it. So that's where you need additional one. This one is, we can use, let's say if we reduce this by 1, that would be the curve sort of we demonstrated over there. But because we need to close this, then we need even 1 more point. Okay? Because even, remember how when we move from the regular vertex to the curve vertex, even with regular vertex, for a triangle, you actually need to provide 4 vertices. That's the first one, second one, third one, and you need to provide the first one again. That's where the additional one is. So in order to close it, you need to provide the first one again. And when it comes to curve, you need to provide, essentially you need to provide 2 additional one on 2 sides, because this thing is circular, so it doesn't really matter the order. As long as you provide 2 more in the same circle, then it will complete the curve. Okay. Yeah.
Yeah.
Okay. And maybe I'll try to explain this with the whiteboard. Let me try to explain that again. So we have a triangle. Let's say we are trying to create a curve on this triangle, and we are starting from here, and we are ending here. Okay? So the first vertex, so this is the first vertex that which provide first vertex, and then the second vertex, and the third vertex. So in order to create a curve, you need at least 4 vertex. Okay, and then this also is the 4th vertex. When you have the 4 vertex, it will create a curve around here. So if you only provide 4 vertices, this is the curve you will see. And now if you provide a 5th vertex there, it'll create a curve here, because now the fifth curve helped to guide the previous vertex. Okay, and now you add an additional vertex here, that's where it finishes. Triangle. Okay. Does that, yeah, hopefully that helps. And so let's get back to this. Now I'll change this back to curve vertex, and this +3. I'm now going to use this equal sign. Okay, so that's a triangle. And then 4 vertices, 5 vertices, 6 vertices, however number you want. Maybe we'll just do something around 10. 10 is almost looks like a circle. But finally, how do we add the noise? The noise can simply add to the radius. So essentially, around the circle, you have a different radius, and that's how it can move, like a blob. Again, we have 2 radiuses here, so instead of changing both of the value, we can simply provide a variable, let radius equal to 100, and then swap these two 100 to radius. So for now, the same thing. So instead of radius, we can multiply that radius by a noise function. And that noise function will have input of based on I. If you simply use I, this will actually not work. Okay? And also it's become smaller because, again, the noise never quite reached the 1. So maybe 200. Okay? You see how it never closes. Yeah, every time we refresh, it never closes. And that's because if I simply use I as an input, the output of the noise function, it changes all the time. So you cannot make sure that the output for I equal to 0 and output for I equal to the number of vertices plus 2. You can't make sure that those two numbers matches, because that's just two sort of random number. Essentially, it's this noise function provide output that changes smoothly, but it's only smooth between the two values that next to each other. But because you are starting from I and ending at a different number, those two numbers is not necessarily same or close. And that's how we have this result here. Okay? So instead of getting the noise value on a linear axis, you want to get the noise value in a circle. And that's where it gets interesting. So essentially, you want to, instead of reading that value from 0 to, let's say, 100, you want to read the value from, on a circle, again, imagine this, there's a grid of noise that you're trying to get the value from. You want to get the first noise value from here, and then second one here, and so on and so forth. And the last value you want to get is also the same spot. So you want to access value with a circle, which again is the same sine and cosine function that we will be using. So sine that map, we essentially will need to use the same map. So sine map I0 number of vertices. So basically map this I from 0 to numbers to 0 to 2 pi. And then cosine and the same thing. Okay? And let me try to tidy code. And this is where, as I mentioned, it's symmetrical because sine and cosine gets to the negative space of the noise. So essentially, the circle that we are drawing is around the origin 0 and 0. And let's see, where was my whiteboard? Refresh this. Okay, so we have a noise space. Essentially, you can provide any x and y coordinate, and this function will provide what output you can get. That will be smooth. However, if you use, the sine and cosine that I mentioned, you are drawing a circle right here. So when you ask for a value on the top right and a value to top left, that the noise function will give you the same value. That's just because the noise function is symmetrical on that space. So instead of that, you want to access the circle in only the positive space. Okay. I mean, in the computer graphics, of course, it's more like I can't actually do undo, but yeah, it's more on the other direction. But anyways, what we care about is that the input for the noise should not be negative. So I can simply 1 plus sine and 1 plus cosine. That makes sure, I mean, again, if you want something that's symmetrical, that's completely fine, but I'm looking for more natural blobs. Okay, so every time we refresh, finally, we're able to create a blob. Yeah, and how do you make it move? You add the z-axis, which is going to be frame count, and it's going to move. Okay, on noise, we're going to add frame count divided by 50, and here we go. Yes.
Can you please repeat the part how you created the blob using the noise function?
Refresh. So the way sine function works is that if you provide x, it outputs a y, and the sine wave looks like this. Okay, so whenever you provide x, it gives you what the corresponding y value is. Okay, and the noise function, when you have a 1D noise function, whenever you provide the noise function, may be something like this, and whenever you have provide x value, I think I can change color. Oh yeah, whenever you provide the x value, it will give you the corresponding y value. That's how the noise works. So this is 1D. What I meant by 2D is that, you have a noise function. We've demonstrated how it's like a grid. Imagine they can be infinitely divided. And in this space, this is x, this is y. In this space, you can give any coordinate, x and y. It will give you a value, of the, in the previous sketch we've done, it's the darkness. But essentially the input can be x and y, it will give you output. And the reason why the first time when we try to create the blob, it doesn't connect is because we are only providing one input. That means it's linear. So essentially we started with a value from here, start from a value here, and end at a value here. So you can't be sure that the two values are close or the same because it's linear. They're just two random locations. However, in order to make sure that the two ends actually has the same value, you need to access the noise in a circular space. So let's start from here, the first value, and then the next value is here, and then the next is here, next one, all the way around. So the last value you get is going to be the same value. Okay, and in order to access this, so essentially the input we provide is x and y. The x and y needs to be in a circular space. And how do we do that? That's when we use the sine and cosine. So when we use sine and cosine, essentially we get a number that's in a circle. So here, I is a number from 0 to number of vertices. It's converted to a number that's 0 to 2 pi. So essentially, when I equals to 0, sine equals to 0 as well, right? So when I is 0, it's converted to 0, and the result for sine is also 0. Okay, because the sine function it looks like this, so it's 0. Yeah. So and then when I equals to the largest value possible for I is 2 pi. When I is 2 pi, it's also 0. So that's how it connects. So that means when I equal to 0 versus when I equal to 2 pi, you are essentially providing the same input for the noise function. That's why you get the same output as well. I don't know if that helps, Adam.
I mean,
Does that?
as the input is the same.
Yeah, so if you have the same input, it will produce the same output.
That's where we're connecting the two dots.
Yeah. This is the end of the workshop series. And what can you do, after this workshop? Here I have a couple of suggestions. So first, on the official website, there's one link to Learn. That's where you can see a lot of tutorials, including the very basic one, getting started, and how to use various things with P5.js. So that's one resource you can use. And two, as I've mentioned before, there's this YouTube channel by Dan Schiffman, which has a ton of video resources, and his video is very beginner friendly. So especially if you are new to coding, I guess we gotta leave in a second. So especially if you're new to coding, I recommend this. I don't know if it's a drill or. Did anyone receive email about the drill, or is it not a drill? Okay. So I'll quickly finish this. So we have this resources Start Learning here. That's if you're new to programming, it goes over the basics of programming in P5.js. And then, of course, this is my Instagram. Feel free to follow and check, my daily sketches.
Let's get started.
Oops. Oh, there you go. Yeah, Dan Schiffman right there. And yeah. Okay, thank you all for attending all my workshops, and I hope to see you around on campus.